Before we introduce the session, I would like to just cover a few housekeeping items. First of all, please silence all your cell phones so that we do not distract the president, the presenter, and others in the class. FNA is officially videoing each session for attendees to view once they have been produced after the conference. We ask everyone to please refrain from taking pictures of PowerPoint slides or videoing the presentation. If we do see anyone taking pictures or video, we will ask you to put your camera away, so please respect this request. Lastly, there are QR codes on the walls. We asked you to do no more paper surveys this year, so we have the QR codes on the walls to do a survey of the session. Once the session is over, we would appreciate you take a few minutes to complete the survey. This will help us improve our future technical presentations. Each survey session survey you complete enters you for a drawing for a $100 Amazon gift card. A little incentive there. So on to our session. The title of our session here is Low Pressure Carbonitriding, a Practical Hardening Option. Carbonitriding is a case hardening process that provides surface layers with superior wear resistance in steels and with limited hardenability. As a low-carbon emissions alternative to atmospheric carbonitriding, low-pressure carbonitriding was investigated and a recipe optimized for common steels in a case study which will be presented and discussed. Please help me welcome our speaker, Mr. Don Marteeny, please.
Good morning, everyone. Thank you for joining us. So, as Rick mentioned, we're going to spend a little bit of time today talking about carbonitriding with a slight twist, if you will, in that it's a low-pressure version. First, though, before we get into that, we'll do a quick overview of carbonitriding just as a refresher. Talk a little bit about low-pressure carbonitriding specifically. Then look at the different equipment that would be used versus a traditional carbonitriding process. And then, as Rick mentioned, look at a specific case study. So, carbonitriding. Unlike maybe some of you attended the first session where Jack Kaluki mentioned or discussed ferritic nitrocarburizing, which is a nitriding-based process. Carbonitriding is a carburizing-based process meant for case hardening. But in this case, we're tweaking it a bit because we add nitrogen. How? We add ammonia right to the process. So in the process of doing that, we're allowing the ammonia to dissociate. In the normal atmospheric process, we would employ endogas as the carbon source, ammonia as the nitrogen source, and this would all be done at atmospheric pressure. On the other hand, low-pressure carbonitriding uses acetylene as the carbon source, ammonia, again, as the nitrogen source, but this time we do it in a vacuum. Looking at a few more differences between the two processes, atmosphere typically tends to be a rather long process, typically run between upper 1600 to lower 1700 degrees Fahrenheit. To maintain a quality atmosphere in the furnace typically needs some conditioning prior to the process and requires continuous process monitoring. Also, because of the fact that we're doing this at atmospheric pressure, there's always the opportunity for some oxygen infiltration and therefore potential for IGO formation. And because we continue to run the furnace all the time, as a matter of course, we have some effect on the furnace component life. From a safety perspective, of course, too, there's also some risk in it's a flammable atmosphere, and because of that, there's risk of fire and explosion. But moreover, and which is becoming a more popular discussion today, is the emission of CO and CO2, which I will come back to in a moment. On the contrary, with the low pressure process, we can typically tune it to be a somewhat faster process. Now, I say up to 1100 C. Now, I want to footnote that with the fact that most of the normal carburizing steels, which this may not necessarily apply to, we typically would limit to around 980 C just to prevent some extreme grain growth in the process, but we'll come back to that. Because we have no environment in the furnace, there's no gaseous environment, there's no real opportunity for IGO formation, which is a plus to this alternative. There's minimal process gas usage with each run. No atmosphere conditioning. The furnace is off when we don't need it. It's on when we do need it. We don't need to continue to run the furnace, which also helps with the fact that we don't have to wear the furnace when we're not using it. Also, because there's no oxygen in the furnace, there's no real risk for a flammable atmosphere, and because of that, no risk of fire and explosion. But, as I said and alluded to, as we continue to be more and more aware of the impact of each process on the environment, this topic is very important. And in the low pressure process, there's very little, if any, emission of CO or CO2. As a comparison, if we take a typical atmosphere carburizing process as a base, before we add the ammonia to the process, just on the endogas side, we're producing, say, around 530 cubic feet an hour for the process, which leads to about 13.5 pounds an hour of CO2 produced, and that's about 55 tons per year of additional CO2 just to run the furnace. Low pressure carburizing, 0. So, as I mentioned, this is becoming a greater and greater topic as we move forward with the changes to our climate, and this is a key aspect of LPC and LPCN. Now, not only is there process variation, but there's also equipment variation. As I mentioned, this is not an atmosphere process, but a vacuum process. So what do we use to complete LPCN or run LPCN? Here's a couple examples of typical, horizontal and vertical single chamber furnaces. Now, one might consider that, yes, most of the steels that we're using for LPCN aren't typically very easily hardenable. Gas quenching may not work for all applications, but if it's a thin cross-section, fairly light mass for each part, LPCN is possible in a gas quenching environment, especially with the fact that this particular setup can go up to 25 bar. So as long as the quench rate is fast enough, it can be done. And as you see, we've got fairly a wide variety of different configurations available. Now, as I mentioned about the quench rate, it may not work with gas quenching, so we have to step to a secondary configuration using a double chamber furnace to add oil to the mix, if you will, where we can handle heavier cross-section parts and more massive parts and achieve the required hardness. So here's an example of those, which we can also do in the gas quenching mode as well with this configuration, and again achieve a slightly higher quench rate than we would in a typical single chamber furnace. And here you'll see a cross-section of both chambers. The other advantage to this is that we're holding this chamber at temperature at all times. So there's no wait for heating and cooling. It's just a matter of introducing the part here into the process chamber for LPCN, back out, quench, and out. So we can remain at temperature, saving some time in the process. If this configuration, or excuse me, a two-chamber furnace doesn't produce the required cycle time, we also have another option, and that is a triple chamber furnace. The advantage here is, again, we can do both gas and oil quenching configurations, but you'll note the addition of the preheating chamber here. And what this does is it allows us to take advantage of the time that we would lose in heating the part in the process chamber, the center chamber, here. And that ends up giving us almost a 2-time productivity increase over the alternative, which improves the overall throughput of the process. So again, this is for high production rates and allows us to improve our overall capacity. And then, of course, there are some other more specialty type scenarios. One is a pit type vacuum carburizing furnace, obviously for more massive parts, that can be arranged with a traditional oil quenching or water quenching setup. The furnace can be open hot so we can remove the part, move it to the quench chamber, quench, and then reload the furnace at temperature. Difference here is that it's a fiber line furnace with metal heating elements. Then there's also a hybrid atmosphere oil quench with vacuum heating chamber solution. Here it's a combination of a standard IQ style quench chamber mixed with a vacuum heating chamber. So it works a lot like the two-chamber vacuum oil quench that we discussed earlier, except the fact that this chamber does not operate under vacuum, but rather atmospheric conditions, using nitrogen, of course. But again, what the advantage here is that you get the vacuum heating option and can conduct low pressure carburizing or LPCN either in that chamber. And then of course there's a more straight through process or single piece flow process available that allows us to produce parts on a more massive scale, 500,000 to 1 million parts per year, and also gives us the ability to trace each and every part, which in some applications is very important for quality assurance purposes. So now, that being said, moving on to an example, a hypothetical example of using LPCN. So carbonitriding, typical temperatures, again, for use with low and medium carbon steels with low hardenability. Typical process temperatures, somewhere between 1380 and 1650. In this case, we're going to look at a process that was done around 1650 F, again, in a low pressure carbonitriding scenario where we're adding ammonia during the diffusion stage and pre-cooling. And as you see here, this is a process trend, if you will, from the simulated cycle. Here you'll see the main heating section, and then the section where we're introducing ammonia during the boost and diffuse portions of the process. Typically, the nitrogen concentration for this type of application, we want to be somewhere around 0.3 to 0.4% by volume. As a result, using, like I say, a low hardenability steel, such as 1015, we can note a few key differences. First, as was alluded to in the previous presentation, we can see a slight improvement of the average coefficient of friction in a more practical sense. What does that mean? We have a more uniform and harder surface than typical carburized surface is concerned. You'll note here that in this plot, the green dots indicate a hardness profile post LPCN, while the red dots indicate a hardness profile post LPC. And then also looking at the microstructure plots, you'll notice a slight increase in the non-martensitic transformation in LPC versus LPCN. Okay, so here we're looking at a real case study, some automotive pulleys that are basically a 1018 steel, again, a low hardenability steel. We're going to run LPCN in a two-chamber oil quench furnace. The parts in this case are typically carbonitrided in an atmospheric furnace. The requirements for roughly a 12 to 16 thousandths case depth and around a key surface, or excuse me, target surface hardness of between 700 and 875 Vickers, or roughly 83 and 84.5 Rockwell. In doing that, we first simulated the process using a simulation tool for low pressure carburizing to set up the initial recipe, if you will, and to gauge the required carburizing and diffusion cycles. Here is the predicted carbon profile from about 0.73 at the surface to about 0.72 at the projected or expected case depth. And then here's the surface carbon trend as we move through the the process itself. With that, here is a microstructure of the SEM of the end microstructure. The one on the left is at 500 times magnification. The one on the right is at 1,000 times magnification. As you'll see, the results are mostly martensite with a small amount of retained austenite, but for the most part, we've achieved our goal, and we've reached a surface hardness of roughly 82.5 to 82.8 Rockwell A, or between 750 and 770 Vickers. And we've achieved a case depth of around 0.33 to 0.35 millimeters, or around, again, our target case depth at the beginning. It's important to note, too, that, again, this was done with an oil quenching furnace, so we've met the requirements. Again, sometimes for lighter parts, gas quenching can work in this application, but typically the best scenario is to use an oil quenching furnace. So, with that said, a few conclusions. First, carbonitriding can provide a viable alternative to other case hardening methods. Low pressure carbonitriding is an equivalent process that can provide an alternative, a zero CO2 emissions alternative to carbonitriding. There's a variety of furnace configurations available, so the equipment is not a limitation for this. And low carbon steels can be improved to meet higher hardness requirements without CO2 emissions. And with that, I just wanted to acknowledge a couple of my colleagues that helped me with this. Dr. Agnieszka Brevko-Stanilevich did the actual case study work, and then Lukasz helped me with a few of the presentation preparations. And thank you very much.
Thank you, John. I'm going to take some questions from the floor, if anybody has any questions. Sir?
Yep.
Your nitrogen, are you measuring how much nitrogen you have at depth?
So that analysis was, to my knowledge, we didn't do that close of an analysis on this particular run, but I think we may have in the past. I'd have to check.
Okay. How do you measure that?
I would be with a mass spectrometer, but I'd have to dig into that for sure. Mm-hmm. Yes, sir.
Also, how deep can you go with case depth? Can you get 150,000?
No, I think that would probably be a bit of a stretch in this case. It's mainly a more shallow case depth application.
Why is that?
I think mainly for the diffusion of the nitrogen into the surface of the steel.
Well, I mean, 150,000 is carbon.
Oh,
Probably 50,000 with nitrogen.
yes, 150,000 with carbon. Yes, I think that could be possible.
But like 50,000, you see the effect of the nitrogen?
Yes, yeah, it would be limited on the effect of the nitrogen.
What do you mean?
So we'd have to extend the overall process to reach the deeper case depths, of course, but I'm saying that the nitrogen effect may not be as deep as 150,000, right? So,
No, I mean, 150,000 is case depth on your carbon.
yes,
About 50,000
yes,
depth on your nitrogen.
yes, that's the limit.
Any other questions? Sir?
Is it more difficult to predict the evolution of the case depth with low pressure carbonitriding compared to LPC?
Yes, it's a newer process. There's been interest in the marketplace for LPCN, so we're experimenting with it now, and this is just the beginnings of that experimentation. LPC is a more well-established process that's been studied, and as a matter of fact, you know, the simulation that we showed here illustrates the point that we understand the surface dynamics, you know, the chemistry at the surface at a much higher level than LPCN. Mm-hmm. Yes, sir.
So you're doing your carburizing, you're doing your boost, you're doing your carburizing, you're not adding your ammonia until the end.
Yeah, until the very end.
So
Yeah.
you're dropping down and you're running a limited time.
Yes,
for your ammonia?
even into the pre-cooling stages before quench. That's right. So it's at the very tail end of the cycle.
Have you ever added ammonia at the beginning to get it deeper into, help get it deeper into the carburizing?
Not to my knowledge, no. No. But that's a good question, and maybe another place to go with further work is adding it earlier in the process.
Any more questions? No, thank you very much.
Thank you very much. Thank you all. Thank you for your time.